Here we're going to look at a nice problem from this book that I really like. So it's called Sacred Mathematics, and it is all about Japanese temple geometry. And the problem we're going to look at today goes like this. We've got a circle of radius 1, and then inside of this circle, we have an equilateral triangle, which I haven't drawn. But then each line segment that is building this equilateral triangle is defining an ellipse. And those ellipses are inscribed inside of the circle, and they are all tangent to each other. And what we want to do is find the maximum area of one of these ellipses. Okay, so let's get to it. So the first thing that I want to do is put everything inside of the coordinate plane. So I'll make the so-called center of this bottom ellipse the origin. Then my x-axis is going to go along this way. My y-axis is going to go along that way. Great. And my first goal is to get an idea for what the center of this circle is. So I'm going to call the center of this circle 0, y naught. And while I'm at it, I can write down some equations of this circle and of this bottom ellipse. So let's first notice that this circle has an equation given by x squared plus y minus y naught squared equals 1 squared, because it's a circle of radius 1. And then next, this bottom ellipse has an equation of x squared over a squared plus y squared over b squared equals 1, where this point A is along the x-axis and this point B is along the y-axis. So that's giving like our major axis and our minor axis. Now let's see what we've got going on here. So we've really got 2 degrees of freedom that are defining this ellipse. So a major axis and a minor axis. So we can get rid of one of those degrees of freedom by making the rule that these 3 ellipses are inscribed this way inside of the circle. And then the maximization procedure will get rid of the other degree of freedom, giving us an actual maximum area of this whole setup. Okay, so our first goal is to get a handle on A and B, or maybe some relationship that A and B must satisfy. And the way we can do that is via the center of this circle. So here I'll draw a line segment, or really it's a line from the center of this circle that is tangent to these 2 ellipses. The important thing is that it is tangent to this bottom ellipse. And what we'd like to do is find the slope of that line. But if I continue this into a triangle, so maybe I'll continue that into the triangle like this. I'll call this height right here maybe delta y, and this length right here delta x. So my slope of this line is delta y over delta x. And then looking at this, along with the fact that we have an equilateral triangle built out of these points of tangency, and this is the center of the circle, we know that this angle measure right here is 30 degrees because it's half 60 degrees, half the measure of one angle of an equilateral triangle. But that tells us that slope of this line is delta y over delta x, but that's going to be tangent of 30 by some trigonometry. So let's maybe go ahead and write that down. So this line that we have has equation y equals tangent 30 degrees times x, and then plus this y-intercept, which is y naught. Good. And so that's by that discussion that we made over here. But tangent of 30 degrees, that's a commonly known value. That's going to be 1 over the square root of 3. So this is 1 over the square root of 3 times x plus y naught. Next, we'll insert the equation of this line into the equation of this ellipse in order to find this intersection point of this purple line with this bottom yellow ellipse. Notice that this tangency means that there's actually only one intersection point, which we'll make use of as we move forward. Okay, so like I said, we're going to plug this value of y into the equation of this ellipse. So that gives me x squared over a squared plus 1 over root 3x plus y naught quantity squared all over b squared equals 1. Maybe I'll go ahead and get rid of my denominators here. So I'll multiply both sides of the equation by a squared times b squared. I think that's going to simplify some things. So that'll leave me with b squared times x squared plus a squared times 1 over root 3x plus y naught squared equals a squared times b squared. So again, I just cleared the denominators there. Okay, next what I'll do is multiply out this binomial squared. That's going to leave me with b squared x squared plus we'll have a squared over 3x squared. So I'll distribute this a squared through while we're at it. And then plus 2a squared y naught all over root 3. So that comes from the cross term there. And then that is times x. And then finally plus a squared times y naught squared. That's going to be equal to a squared times b squared. Good. Now, if I look at this, I've got a quadratic equation in x, which is super helpful because that's going to help us find the x coordinate of this intersection of that tangent line with this ellipse. But in fact, we're not going to worry about finding that x coordinate. We're going to use the fact that there is only one such intersection point. But if we've got a quadratic equation with one such intersection point, we know that that means that the discriminant of this quadratic equation must be equal to 0. But let's recall that the discriminant is the term which looks like b squared minus 4ac. That needs to be equal to 0. That comes from the quadratic formula. But before we can see what that is, we really need to put this in the form of ax squared plus bx plus c, where maybe I'm talking about capital A, B, and C here, just so it's not a confusion. So let's maybe combine like terms, look at what our coefficient of x is. That'll be b squared plus a squared over 3. That's our coefficient of x squared. Then our coefficient of x is this guy right here. So that's 2a squared y naught over root 3. And then our constant term, after moving this over, is a squared y naught squared minus a squared b squared. So we have all of this is equal to 0. So next, viewing this as a quadratic equation in x, so this is like my coefficient capital A, capital B, and capital C. From our earlier discussion where this has only one intersection point, we know that our discriminant is equal to 0. So in other words, our b squared minus 4ac is equal to 0. Okay, so we've got our capital B squared. So that is going to be 4a to the 4th y naught squared over 3 minus 4 times a times c. So that's going to be minus 4b squared plus a squared over 3 times a squared y naught squared minus a squared b squared. All of that needs to be equal to 0. So next I can divide both sides of the equation by 4. That'll allow me to cancel this thing right here and this thing right here, which is good news. And then we can work towards finding y naught in terms of a and b. Maybe along that goal, let's multiply out this right-hand term. So I'll just bring this term down. So we'll have a to the 4th times y naught squared over 3 minus, so let's see, we'll have a squared, b squared, y naught squared. That'll be our first times our first. Then next we'll have minus a squared, b to the 4th. That'll be our first times this one right here. And then next will be plus a to the 4th times y squared over 3. That'll be this term times this term. And then finally minus a to the 4th b squared over 3. Great. So that's what we end up getting, and all of that is going to be equal to 0. So let's first notice that we can cancel this guy out with this guy, given that they have opposite signs after distributing this minus sign. So we'll get this cancels with this. So that's pretty good news. But that means all of the rest of the stuff in parentheses must be equal to 0. So we might as well multiply both sides of the equation by a minus sign to cancel that into a plus. And then next we can solve for y naught pretty easily. So let's see what that will give us. So we'll have a squared b squared y naught squared equals, so moving this stuff over, we'll have a squared b to the fourth plus a to the fourth b squared all over 3. Okay, next we can maybe divide both sides of the equation by a squared b squared, and that's going to give us y naught squared equals, so here we'll have b squared plus, and then here we'll have a squared over 3. Good. So that is our y coordinate. So the fact that we are placing this bottom ellipse so that its central point is at the origin, depending on the size of our major and our minor axis, that's going to shift this circle up and down the y-axis. And so that's why this y coordinate, which is the center of our circle, is going to depend on the major and minor axis. Okay, so let's maybe take this data, we'll bring that to the top, and then we'll move on to the next step. Let's see where we are. We've got our equation of our circle that has center 0, y naught, the equation of our ellipse, the equation of this line, which is purple over here, and then we have an equation that describes the relationship between y naught, a, and b. So we've got y naught squared equals a squared over 3 plus b squared, and we got that by the intersection of this line and the ellipse using the fact that it only intersects at one point. Okay, so next what we're going to do is use the intersection of the circle and the ellipse to get some more data about a and b. So notice we've got this equation of the circle, we've got this equation of the ellipse. That allows us to maybe reduce this equation of the ellipse to only one variable. Maybe we'll have the variable be equal to y because it's pretty easy to solve this thing for x. So let's see what that gives us. That gives us 1 minus y naught squared over a squared plus y squared over b squared equals 1. So again, what this is helping us do is calculate the y coordinate of the intersection point of this ellipse with our bigger circle. So that'll be like this point right here or this point right here. But notice those have the same y coordinate, just different x coordinates. Okay, good. But since this is an equation for y, this should also have only one solution, which means we can use the same trick that we just did. But before we get to that, let's maybe manipulate this a little bit. So I'll first multiply both sides of the equation by a squared b squared. So that'll leave me with b squared minus b squared times y minus y naught squared plus a squared times y squared equals a squared b squared. Now, again, I've got a quadratic equation for y, and I can rewrite that so that it's a little bit more helpful in order to use a quadratic formula and another argument involving the discriminant. So let's see what we can do to do that. Maybe we'll quickly multiply this out over here, giving us y squared minus 2y y naught plus y naught squared. Then we'll move this guy over to the other side of the equation and then collect our y squared terms, our y terms, and our constant terms. So let's see what our y squared term is. So we've got a y squared attached to this, which is a squared. Then we've got a y squared attached to this, which is minus b squared. So we have a squared minus b squared. That's going to be a coefficient of y squared. Now let's look at what our constant term, our linear term is. So that's the coefficient of y. So that's going to be minus 2y naught times minus b squared. So that is plus 2y naught times b squared times y. Good. And then finally, let's see what our constant term is. So we'll have a minus b squared times y squared. Y naught squared, I should say, and then a plus b squared, and then a minus a squared b squared. Great. So that's all going to be equal to 0. Now, if we think about this as playing the role of capital A in our quadratic equation for y, this is playing the role of capital B in our quadratic equation for y, and then this thing right here is playing the role of capital C in our quadratic equation for y. Again, we know that our discriminant must be equal to 0 because there is only one y value for which this bottom ellipse intersects this circle. So let's see what that gives us. So again, we'll have capital B squared, so 4y0 squared times b to the fourth, and then minus 4 times capital A, so that'll be a squared minus b squared, times capital C, which is this thing right here. So that's going to be minus b squared y0 squared plus b squared minus a squared b squared. And again, that needs to be equal to 0 because our discriminant needs to be equal to 0. So next we want to manipulate this so that we can solve for y0 squared and compare this value of y0 squared with our earlier value of y0 squared. But maybe first we can notice that we can cancel a 4 from this term and this term just by dividing both sides of the equation by 4. Next, we can multiply things out. So we'll have y0 squared times b to the fourth. Okay, so now multiplying this a squared through, let's see what that gives us. So that'll give us minus a squared b squared y0 squared. And then we'll have plus a squared b squared. And then finally, we'll have minus a to the fourth b squared. The next, we want to multiply this minus b squared through. That'll give us plus b to the fourth y0 squared. And then next, minus b to the fourth. And then finally, plus a squared b to the fourth. That all needs to be equal to 0. So let's see if we can cancel anything. We've got a y0 squared and a b to the fourth here. Then minus all of this stuff in parentheses, which includes a y0 squared b to the fourth. So that cancels as well. Next, we have minus all of the stuff in parentheses equals 0. So that means we can cancel this minus sign just by multiplying both sides of the equation by minus 1. And then we've got all of this stuff in parentheses is equal to 0, but only one of those terms has a y0 squared in it. So let's maybe rewrite this and so that we have solved for this minus a squared b squared y0 squared. We can maybe add that to both sides of the equation. That gives us a squared b squared y0 squared equals. So next we'll have a squared b squared minus a to the fourth b squared minus b to the fourth plus a squared b to the fourth like this. Finally, we'll divide both sides of the equation by a squared b squared. That'll leave us with y0 squared equals 1 minus a squared. That's what we get from that. And then next, it's going to be minus b squared over a squared. That's what we'll get for this term. And then finally, plus b squared. That's what we'll get for that last term. So that gives us another expression for y0 squared. So I'll maybe go ahead and bring that up and we're almost to the end. We just got done calculating y0 squared two different ways. One by intersecting this line with the bottom ellipse and one by intersecting this circle with the ellipse. So we got these two quantities, but that gives us a relationship between a and b, but really more a squared and b squared. So I'm going to exploit that to maybe rewrite a in terms of b or b in terms of a. So I'll set those two blue underlined things together. So I'll set those two blue underlined things equal to each other. That gives me a squared over 3 plus b squared equals 1 minus a squared minus b squared over a squared plus b squared. Now, first things first, I can cancel this b squared with this b squared. Then next, maybe I can clear the denominators on both sides of the equation by multiplying by 3a squared. So let's see what that gives us. That'll give us a to the fourth. So that's multiplying this by 3a squared equals 3a squared minus 3a to the fourth. And then finally minus 3a squared b squared. So that's what we get for all of those parts. But let's see where we can go from here. That's gonna give us, we can add this to both sides of the equation. So we'll have 4a to the fourth equals 3a squared and then 1 minus b squared. So that's what we get from factoring a 3a squared out of each of those. Then next we can divide both sides of the equation by a squared. So that'll cancel this one down to a 2. And then finally, that leaves us with a squared equals 3 times 1 minus b squared all over 4. So those are the appropriate values of the major and minor axis with respect to each other in order to put this inside of the circle in the first place. Okay, so now that we have this relationship, we can move towards maximizing the area of one of these ellipses. So far, we've determined that in order for these ellipses to fit inside of the circle, we need the major and minor axes to be related like this. So a squared equals 3/4 1 minus b squared. So next, we'll use the fact that the area of the ellipse is pi times a times b. So that's the major axis times the minor axis. So that's the same thing as pi times the square root of a squared times b squared. So that may seem not super helpful, but notice our expression here is in terms of a squared, so that is pretty helpful. So let's see, in our setup, that gives us pi times the square root of 3/4 b squared times 1 minus b squared. So now our goal is to find a b that will maximize this equation. Okay, so let's look at this. Notice that finding a b that maximizes this equation is the same thing as finding a b that maximizes the interior of the square root function. And that's because the square root function is an increasing function. So in other words, we want to maximize the equation, maybe I'll call it f of b, which is 3/4 b squared and then 1 minus b squared, like that. But I maybe want to point out here that we don't really need a 3/4, and that's because we'll get the same maximum value for b whether or not the 3/4 is in there. Remember, we just want the value of b here. Next, we'll expand this out and then use some calculus. So notice multiplying the b squared through gives us b squared minus b to the fourth. Then next, maximizing this will be equivalent to finding where the derivative equals 0. So the derivative here with respect to b will be 2b minus 4b cubed. We want that to be equal to 0. So notice we can maybe divide both sides of the equation by 2b, and that'll give us 1 minus 2b squared equals 0. But that means that 2b squared is equal to 1, which tells us that b equals 1 over the square root of 2. Okay, but if b is equal to 1 over the square root of 2, we can find out what a is as well. So notice a is going to be equal to the square root of this object. So it's the square root of 3/4 times 1 minus b squared, but 1 minus b squared is 1/2 here. So we get something like that. Okay, so that simplifies actually quite nicely to 1/2 times the square root of 3/2. Nice, so we found our major and our minor axis measurements that will create the maximum area of this ellipse. Now we just have to calculate that maximum area. So let's see what we get for that. So this area, like we said up here, is going to be equal to pi times a times b. So that's going to be pi times this times this. So let's see, that'll be pi times the square root of 3/4. And that's a good place to stop.